Laplace transforms will give us a transformation that will allow us to change a differential equation into an algebraic equation. So we're going to have something like maybe a second order differential equation. Something like a second order differential equation that we're going to convert into an algebraic equation. That we'll be able to solve. Hopefully we'll be able to solve. Once we get the solution to the algebraic equation, then we'll do a conversion back into differential form. So we're going to start with a differential equation. We're going to convert it to an algebraic equation. Solve the equation algebraically. And then convert back to the form that we need for the differential equation. Now, the Laplace transform will take a little bit of work, but the transform itself is really just an integral that gets applied. Here's the definition. A Laplace transform is defined as L. This is the symbol. Most of the time, this L is a fancy L. I couldn't find one when I was working with my equations, so it's here it just looks like an L. But most of the time it's a fancier looking L like this. L of some function of t is equal to an integral as t goes from 0 to infinity, e to the negative st times that function, and you're integrating with respect to t. Now, there are many tables of Laplace transforms, but it's important that you know actually how to find the Laplace transform. And so we're going to look at a couple of functions finding the Laplace transform by applying this definition. On the first one, we're going to start with a nice constant function. F of t is equal to 1. And then the Laplace of 1 using the definition. The Laplace of 1 is an integral from 0 to infinity, e to the negative st times 1, integrate with respect to t. And when you do this integration, multiplying by 1 just gives you e to the negative st. And we're integrating with respect to t, so this s is considered a constant. And so really you just have e to some constant times t. When you integrate an exponential with a linear exponent, you get that same exponential back, e to the negative st, divided by the coefficient, divided by negative s. And we don't need the plus c here because we have a definite integral. We're given these limits. And so we want to evaluate this for our limits. At 0, that's no problem because we can substitute in 0. But at infinity, we need to take the limit. This is the limit as t goes to infinity. And so let me break this up piece by piece. I'm going to have the limit as t goes to infinity of e to the negative st divided by negative s. That's substituting in this limit as t goes to infinity, and then minus, when I substitute 0 in for t, I'm going to get e to the negative s times 0 divided by negative s. So because my limit involves just the t, if I wanted to, I could bring that negative s out. I get 1 over negative s limit as t goes to infinity e to the negative st. On my second term, this minus and the negative in the bottom cancel out to give me a positive. This is just e to the 0 power, which is 1. So that second term is just 1 over s. So what I want to look at here is this exponential function. An exponential function, if I look at a graph of it, this would be my t-axis, and this will be y. And if I look at a graph of y equals e to the t power, well, let me do e to the kt, where k is some constant. My graph is either going to look like this, or, let me change the color. There we go. Or it's going to look like this. And this is 1 right here. Now, what I want is I want this value to converge. There we go. I want this limit right here to converge. And in order to get that limit to converge, I want it to go the way this orange line is going. Go to 0. It's getting closer to the x-axis, or the value is getting closer to 0. And in this case, our k value is negative. K is less than 0. In the other case, k is greater than 0, or positive. Okay, so to converge, to get this to go to 0, I need k to be less than 0. In this case, our k is negative s. So I want negative s to be less than 0. If you divide by negative 1, that tells you that s has to be greater than 0. When you divide both sides of an inequality by a negative, you reverse the direction of the inequality symbol. 0 divided by anything is 0. So if s is greater than 0, then the limit as t goes to infinity of e to the negative st will be 0, and I get 1 over negative s times 0, which is 0, plus 1 over s, or just 1 over s. So I have when s is greater than 0, this converges, and you get 1 over s as the Laplace transform. Laplace of 1 is 1 over s. And there's a condition here that says that s has to be greater than 0. Notice that when s is less than 0, then I'll go back to my graph here. When s is less than 0, then I have this graph that's increasing, and the limit at infinity is going to be infinity. And and this function won't really be usable. You would end up with infinity for everything. So we really want this e to the negative st to cancel out.